Okay, so recall that the space of rationals is second countable since the standard basis for the space, consisting of open intervals from A to B, where A and B are rational numbers, is countable. So let x be any rational number. Then the collection script B sub x, consisting of the open intervals from A to B that contain the point x, is a local basis at the point such that this local basis is a subset of the standard basis for the space of rationals. And so for every point in the space, the local basis at that point is countable, since subsets of countable sets are countable, and hence the space of rationals is first countable. Now, since every finite point set which we'll call F, and the set of integers are nowhere dense in the space, the complements of these sets are dense in the space. Further, these dense sets are countable. Once again, since the subsets of countable sets are countable, and hence the space of rationals is separable. Okay, so new definition. A real number that is not rational is called an irrational number. The set of all irrational numbers is denoted as the complement of the rationals, that is, the reals set minus the rationals. Now, in our construction, of a separation of the space of rationals, and recall that that was the set A together with its complement in the rationals, where the set A consisted of all those rational numbers where that number is strictly less than the square root of 2. Now, in this construction, we can replace the square root of 2 by any irrational number, alpha, and the pair consisting of the set A together with its complement is also a separation. Of the space of rationals. So next we'll prove a lemma. Let Q be a non-zero rational number, and let alpha be an irrational number. Then the product Q times alpha is irrational. So proof. Suppose to the contrary, that the product Q times alpha is a rational number. Now, since the number Q is a non-zero rational number, there exists a non-zero integer A and a positive integer B, such that Q is equal to A over B. Now, since Q is not 0 and alpha is an irrational number and therefore is also not 0, the product Q times alpha is not 0. And so, assuming that this product is rational, there exists a non-zero integer C and a positive integer D, such that Q times alpha is C over D. And hence, we have that A over B times alpha is equal to C over D, so that alpha is the product B times C over A times D, where B is a positive integer and C is a non-zero integer. So the product B times C is a non-zero integer, and A is a non-zero integer, where D is a positive integer, and so the product A times D is a non-zero integer, and so alpha, being the ratio of the product B times C over the product A times D, is a non-zero rational number. And so by contradiction, the product Q times alpha is irrational. Okay, so we'll use this lemma and the previous theorem to prove a corollary. Let A and B be real numbers where A is less than B. Then there exists an irrational number alpha such that A is less than alpha, which is less than B. That is, between any two real numbers, there is an irrational number. So proof. Now, since A is less than B and the square root of 2 is a positive real number, we have that A over the square root of 2 is less than b over the square root of 2. Now since a over the square root of 2 and b divided by the square root of 2 are real numbers, where a over the square root of 2 is less than b over the square root of 2, there exists a rational number q such that a over the square root of 2 is less than q, which is less than b over the square root of 2. Now notice that if q happens to be 0, if we happen to choose 0 for q, then because a over the square root of 2 and q being 0 are both real numbers, there exists a rational number between a over the square root of 2 and 0. And so without loss of generality, we may assume that q is not 0. And so we have, multiplying through the inequality by the positive square root of 2, we have that a is less than q times the square root of 2, which is less than b, where the product q times the square root of 2 is an irrational number, and therefore for every pair of real numbers a and b where a is less than b, there exists an irrational number alpha such that a is less than alpha, which is less than b. So consider the real line that is the set of reals together with its standard topology, which is the order topology. The standard basis for the real line is the collection script B, consisting of all open intervals from a to b, where a and b are real numbers. Let U be a non-empty open set. Then, for every point in this non-empty open set, there exists a basis element such that the point is in this interval, which is a subset of the set U. So for this open interval from a to b, a is less than b. So since a and b are real numbers, where a is less than b, there exists a rational number q such that a is less than q, which is less than b, and hence the rational number q is in the open interval from a to b, and this interval is a subset of the set U. And so for every non-empty open set U in the space of reals in the real line, the intersection of this set with the set of rational numbers is not empty, and hence the set of rationals is dense in the reals. Further, since the set of rationals is countable, the space, the real line, is separable. Now let x be any point in the real line. Then, for every open neighborhood, v of x, the intersection of v with the rationals is not empty, and so there exists a rational number q such that the 2-point set x and q is a subset of the neighborhood v, and so the intersection of this 2-point set with the complement of the singleton containing the point x is a subset of the intersection of the neighborhood v with the complement of the singleton containing the point x, so that the singleton containing the rational number q is a subset of the intersection of the neighborhood v with the complement of the singleton containing the point x. And so, for every open neighborhood, v of x, the intersection of that neighborhood with the complement of the singleton is not empty. And this is true of every point in the space, and hence every point in the space is a cluster point. And so there are no isolated points in the real line. Now, once again, constructing a separation for the space of rationals is a simple process. We simply choose an irrational number alpha, and then all rational numbers in the open ray from alpha to negative infinity are separated from the rational numbers in the open ray from alpha to positive infinity. Now, the rational numbers considered as a subset of the reals that coincide with the open ray from alpha to negative infinity can be represented as the intersection of the rationals with the open ray from negative infinity to alpha. Now notice that this set is bounded above by the number alpha, and in fact the set of all upper bounds for this set is the closed ray from alpha to positive infinity. And so the least upper bound for this set is the real number, the irrational number, alpha, which is not in the set of rationals. If we now consider the entire open ray from negative infinity to alpha, then once again this set is bounded above by the number alpha, and once again the set of all upper bounds for this set is the closed ray from alpha to positive infinity, and so the least upper bound for this set is the number alpha. Now notice the special difference for the real numbers that is not true of the rationals, and that is that the least upper bound, the supremum of this set, is in the set of reals, which is not true for the rationals. Now, it is reasonable to assume that for any non-empty subset of the reals that is bounded above will have a least upper bound, a supremum, that is a real number. But we cannot prove this. We instead ensure that this is the case axiomatically. That is what's known as the Completeness Axiom. And the Completeness Axiom states that for every non-empty subset A of the reals that is bounded above has a least upper bound also in the set of reals. That is, the supremum of A exists and is a real number. We will use this axiom to demonstrate or to prove that the real line is connected.